Okay, first and foremost, the date for the assignment has been postponed, and I will discuss what exactly you're supposed to do. Now, couple of things that you should keep in mind is if you want to do the workspace analysis, you will have to update your MATLAB that is given to you for free. So please update your MATLAB. So we are talking about assignment 3. So update MATLAB to 2024B. Now, if you look at the assignment, I gave you a Fanuc robot. And the Fanuc robot that is inside the MATLAB is not the same robot as the one in the lab. So the Fanuc robot that you have inside MATLAB is 200 IB, right? This is inside MATLAB. And the Fanuc robot that we have in lab is 200 ID, 7L, right? 4S in lab. These two robots, even though they have the same configuration, the link lengths are different. So the 7L the 4S robot is actually has a longer reach than the old robot. Now here is what you should do. For 200 ID 4S, the dimensions are given to you. And in case if you don't know where the dimensions are, that picture is on the cage. So if you have seen, or you can actually go to the Fanuc website, it will give you the specifications for this. There are multiple ways to solve the problem. First, you will work out a forward kinematics problem. So you will solve forward kinematics. And in forward kinematics, at the end of the day, you are going to have 0H6. And in 0H6, you are going to have 0R6, which gives you the orientation of the end effector. And you are going to have Px, Py, and Pz. I don't think you should have any problems in working out the forward kinematics by hand. Everyone got forward kinematics?
So if you're not getting the correct defender from what's expected, is there a good way to troubleshoot from like frame zero to from 36?
Correct. So actually, it's a very, very important question, and I want to answer that in detail. So many a times, what you notice is the industrial end effector or industrial robots, their coordinate system or their coordinate orientation may not be the same as the coordinate system that we have assumed. Example, for an example, you have this Fanuc robot, and for some weird reason, the coordinate system of this Fanuc robot could be somewhere over here. Okay, that is absolutely possible, because here is what you are doing. You are entering the information in the teach pendant. Teach pendant is giving you the output, and you are trying to compare the output from the actual robot with the mathematical analysis that you have done. So now there is always a possibility that you might have assumed your coordinate frame over here, but the Fanuc robot software would have assumed the coordinate system over here. That is absolutely possible. The teach pendant allows you to align the coordinate system to wherever you want. So basically the base coordinate system can be assigned or can be moved anywhere you want. Now, if you want, there is another thing. If you look at the teach pendant, in the teach pendant setup, you have something called as the end of arm tooling, EOA tooling. So what it means is the teach pendant or the robot could be programmed with an end of arm tooling that may or may not exist on the robot. So that is another thing to verify. When you are doing the forward kinematics, if the end of arm tooling is added to the robot or not. Otherwise, you are not comparing apples to apples. Then the question comes, and this is actually a very practical problem. And unless you work with an industrial robot, you will not understand. This has happened to me before, multiple times. Now the question is that whatever software you have written, whatever equations that you have, they don't give you the right answer. So how do you find out what is wrong and where is wrong? So first and foremost, if you want to solve this problem, you would actually have to look at the pieces. Example, and this is extremely important. How did we find out 0H6? We found out 0H6 by 0H1, 1H2, 2H3, 3H4, and so on. You agree with me? Now, if your forward kinematics answer is not matching, the first step, what you should do is, you should find out 0H2. You should find out 0H2. What would 0H2 give you? 0H2 is gonna give you 0R2, and it is gonna give you Px, Py, and Pz for the second frame. Do you agree with me? So first thing, what you should do is, and you have to do it manually. Sometimes the teach pendant will allow you to get, teach pendant can give you those values. But for some reason, if you don't have access to the intermediate joint link positions, you should actually take a scale and measure and make sure that frame number 2 is with respect, the location of frame number 2 is Px, Py, and Pz. Now, imagine you have the issue is what if you have an offset in the ground plane, which means you have a built-in offset. So you can actually just work out 0H1. 0H1 is, for an example, this is your 0th frame. I'm assuming this is going to be your first frame. Now what you do is, you move the robot just the first theta by maybe 30 degrees or 40 degrees. Okay. Use a measuring tape. Use a measuring tape and measure physically the distance between the frame 1 and the frame 0. Everyone understood this? That will immediately tell you first whether your axes are aligned or not. Second, whether your coordinate system or the origin is aligned or not. Everyone understood this? Yeah.
If you don't have the physical model with us, is it safe to use the dimensions of the robot?
No, you have to do this measurement on the robot. Trust me, I have gone through that rabbit hole, and unless you work with the machines, you will not get answers right. So physically, you program the robot, change theta 1 to 20 degrees. See what your answer is. Measure physically where the robot is and ensure that your measurement is accurate with your answer. Start with theta is equal to 0. See if it's working. And then what you do is you go to 0H2. Repeat the same process. make sure that the frame 2 is oriented and it's at the distance px, py, pz. Then you go to 0h3. And finally, you go to 0h6. And when you do this exercise, you will notice, and again, it's a little weird. Depending upon the manufacturer, they use different coordinate frames. The convention that we used in solving the forward kinematics and inverse kinematics, understand, we use rotation matrices. They don't use rotation matrices. They use quaternions. It's a whole different procedure or whole different way of solving the problem. So you have to go step by step to make sure that your forward kinematics answer matches with the physical robot end effector position. Only then you will get the correct answer. And that is the reason why I asked you to do this exercise. Because I have gone through this. You actually program the robot in your software simulation, like a Robo Guide or a Robot Studio, and then basically create the program and you upload the program onto the robot and robot hits something. That has happened to me. And then basically you have ruined the robot. So it's always a good idea to do this incremental approach in step-by-step approach to make sure that even so sometimes the robot manufacturer will give you their software. You program the robot in the software. In software, robot is running fine. That does not mean you take that piece of code and deploy that on the robot. What you do is you basically take a small piece of code, first move the first joint, then second joint, third joint, and go through the entire cycle. Because otherwise you have this $100,000 robot hitting $500,000 machine. And guess what? You'll be out of jobs. So be extremely careful. So that's why, remember, you can't learn how to swim by watching YouTube videos or running simulations, right? You have to jump in the water. So that's why I gave you this simple looking exercise, which means what you will have to do when you go to the lab next time, you have to take measurements again and make sure your analysis is correct. Did that answer your question?
Yes, it did.
Okay. Now the question is, can I measure that with a scale? Sometimes you can, but if you have a tape so that you can actually bend it and then kind of look at all that, that actually is helpful. If you don't have the tape, get a string, attach the string, and then find out the measurement. I've done all that. Even better, if you have your iPhone, now you have this distance measurements. You can measure that using iPhone. So a lot of interesting ideas that you can think about.
So with the measurements, we have to just assume that, like we're looking at from above and then.
The measurements you need to find out if the robot coordinate system is at the same location where you assume your coordinate system is. Second thing, the X, Y, and Z for the coordinate system, they are aligned with the X, Y, and Z's that we have assumed. Otherwise, at every step, you will see the answers would be positive or negative. And don't worry about it. Just add the terms corrected, add positive or negative signs. So go in pieces, step by step. Make sure your first frame is at the correct position at correct orientation. Second frame is at correct position, correct orientation. And you go on from there. And then finally you'll get the correct answer. Yeah, I'm waiting for one more question. Okay.
So how can we do that? Because how can we verify it? Because we only can verify it in the lab, but at home, we only have the equations. We cannot know whether our transfer.
Correct. So when you go to the lab, I'm hoping that you will have a forward and inverse kinematics code working. You would enter forward kinematics angles, program the FANUC robot with those angles, make sure your answers are matching. So that then same thing you will do with the inverse kinematics. So at home, you will write the code, you'll make sure that code is working, and when you come to lab, you will correct or make changes to the code so that the answer on the teach pendant is same as the answer that you obtain from your simulation. Does that make sense?
The linked lens for the fan of robot are not very clearly mentioned, like what can be done?
Where can we get it? Where can we get the linked lens for the Fanuc robot?
So the document that you provided, it had like because it's
There is a big picture of Fanuc robot with the linked lens specified on the cage that is attached to the robot.
okay.
So, when we change the dimensions, that's what I did. I changed the dimensions to make like the same the assignment. But when we go to use the workspace analysis, if you have changed the rigid body tree from a robot, it's not.
No, we'll do the workspace analysis later. First, there is one more question I'm waiting for someone to ask me. If you don't ask, I won't tell you the answer.
Coordinate shifting, like.
No, coordinate shifting, I already answered. Unless you do it, unless you struggle, I can help you. Smooth sailing never makes a skilled mariner. Test of fire makes the finest steel. No guts, no glory. No pain, no gain.
Since we're doing the.
Small changes in linked lens is fine. I mean, that's totally fine. I mean, if your answers is matching in millimeter, you will get answers very close in millimeters. No, there can happen gimbal lock. See, that's why unless you jump in the water, you will not. Even if you do this, you will have another issue. And I have faced that issue in the actual industry. The question is, how do you ensure the orientation is correct? I will let you think about this.
There is a different orientation in each joint, right? When we're searching.
So I have two choices. I can give you the answer, or I will try to find the answer yourself. But I would let you think about it. Life does not come with a user manual. MATLAB doesn't come with all the solutions. Since you haven't had that problem, I would let you first reach to the problem and then help you with the solution. So yeah, I will let you.
The portraits are kind of like the base is there, but the engine factor is aligned different. So the pad is giving X and Z axis in the opposite way.
Yeah. So you can you can go forward. You can do forward kinematics step by step, and you will get the correct answer.
Like invert in the end, from the end to the bottom.
No, you can go from end effector all the way to the coordinate frame. That's also fine. But then you don't know if your intermediate poses are correct or not. So finally, your end effector will be at the same location, but your intermediate joints would be at different location. Okay, I'll let you figure out what happens. There is something else that would happen. Okay, now let me answer the important question. How do you do inverse kinematics? Now, probably you thought that it's very difficult. It's actually not. So the way you would do it is, in the class, I talked about the inverse kinematics IK solution, wherein you have a manipulator and you have a spherical wrist. The baseline assumption here was the final end effector position was given by the manipulator, and final orientation, which is roll, pitch, and yaw, which is your your pitch and roll is given by the spherical wrist. This assumption is valid as long as last three joints are extremely close to each other, which means almost they are on top of each other. Only then this solution would work. Otherwise, you have to use some type of a numerical technique. You have to solve some type of a numerical technique. MATLAB has a built-in function for solving inverse kinematics numerically. And if you go to MATLAB file exchange, you will see lot of codes where people have used built-in MATLAB functions and done inverse kinematics. But the clean way of doing this is using inverse kinematics designer. Inverse kinematics designer. And if you believe what I said in the first class, you can do your forward kinematics and inverse kinematics in inverse kinematic designer in just 1 second. Now here is what you do. Inverse kinematic designer needs the robot configuration tree. Now that is called as the URDF file. So which is called as Universal Robot Description Format. This URDF file contains all the information, the kinematic information about robot. Now MATLAB Inverse Kinematic Designer uses this URDF file to solve for forward kinematics and solve for inverse kinematics. So basically, if you look at the forward and inverse kinematics code, it uses this URDF file. Now, but this is not a visualization. So this will not show you the robot plotting. So you can build your own visualizer, or what you can do is you can use the MATLAB visualizer. So basically, MATLAB has this visualization capability. Now, what I would suggest you do is there are three approaches. First, you can write your own URDF file, which is extremely simple. Write URDF file. Now, how do you write a URDF file? It's just a simple text file. You actually type in the robot parameters. It's very standard. So if you open any URDF file, it will show you where the link lengths go, where the orientations go, and so on and so forth. You can write your URDF file. Second, you can use the DH parameters that we will talk later in the class to generate a URDF file. If you have a solid model of the robot, if you have a CAD model of the robot, CAD softwares like SolidWorks, CATIA, Autodesk Fusion can write a URDF file. So you can use this URDF file and MATLAB Inverse Kinematic Designer to solve forward and inverse kinematics. Now the alternative approach is, please note that inside the Inverse Kinematic Designer, there is already a FANUC robot, which is FANUC 200 IB, right? And you can very easily do forward and inverse kinematics for that FANUC robot. Now, if you click on this FANUC robot, you will see different links. So you can actually click on each subsection or each link that is described in that FANUC robot. It will show you the link lengths. What you can do is you can change these link lengths corresponding to 200 ID. So which means you change the parameters because the configuration is exactly the same. The robot configuration for the 200 IB and 200 ID is the same. Yeah.
All of this is inside the URDF file.
No. What you do is you import the FANUC 200 IB inside the inverse kinematics designer. And I showed that you can go to watch the video. You can go through each and every link in the inverse kinematics designer and it will show you the link lengths. You can change those link lengths, which means you would have the CAD model of 200 IB, but the calculations internally will be done for 200 ID.
Are we able to also update the angles and the limits? and the
Yes,
negatives and
yes,
positives?
yes, you can do everything. So basically, change the parameters of 200 IB so that it matches the parameters of 200 ID. And you would be able to solve the forward and inverse kinematics and you would be able to get the exact same answers. Now here is one more step that I would recommend you do. Now understand, you are working with 3 different systems. You have your physical robot, you have the robot kinematic diagram that you have drawn and found out forward and inverse kinematics. And now you have the robot that is imported in MATLAB and you are using that robot to find forward and inverse kinematics with different parameters. Everyone understood this? The answers are not going to match unless your coordinate systems are aligned. Everyone understood this? Now to answer your question, what I would do is whatever calculations we have done on paper, I would try to do the exact same calculations in the MATLAB software. Provide certain value for theta1. See what angle, what px, py, pz I get. Compare that with the px, py, pz that I get from my forward kinematics. Go to the second frame, find px, py, pz. This exercise is extremely important. Because what happens is there is no guarantee that the software that you are using has the same coordinate frame as your mathematical calculation, same frame as your physical robot. And something is not aligned and your answers will not be correct or they won't match, or worst case, the robot may break. Everyone understood this? So it's not a trivial exercise. What you need to do is when you start using inverse kinematic designer, and if you want to compare the answers from the inverse kinematic designer with the physical robot and your hand calculations, first you have to again make sure you do the hand calculation for H0, H1. Add some value for 0H1, see if the end effector, the frame 1 is at the same location as you get from your mathematical equation. And how do you do that? If you go on to the solver, it will basically give you a drop down menu where you can actually select each frame and find out the px, py, pz and the orientations for each frame with respect to the base frame. Everyone understood this?
So is it the same thing? I just want to verify because I tried that, but it's all over the place. So it's using the same thing, but it's not rotating accordingly.
We can discuss that after the class. So, but everyone else understood?
You know, you say we should be using the leads on the inverse kinematics and change the values. It doesn't work. It doesn't work inside the inverse kinematics. You mean on the management, the matrices, right?
Yeah.
It doesn't let you change.
Show me your code and then I'll see if there is something not right. So basically you can, the second, okay. Now second thing what you can do is, first you can change the parameters. And then, okay, then you have to save that as a different name. You can't just say, because I believe the baseline models, they are only read only. So I don't think they will allow you to update. So you have to save it as a different name. Second thing what you can do is you can actually go down, open the URDF file inside MATLAB. MATLAB has the URDF file and the whole tree for 200 IB. Change this URDF file the link parameters to reflect 200 ID. And if you do this, you don't even have to use forward inverse kinematics designer. You can do it with just the baseline MATLAB function. Now, what you can do is typically URDF file can only solve kinematics problem. But if you need a visualization software, you need to have a CAD model. But as far as this exercise is concerned, it doesn't matter if your CAD model is for 200 IB because it's the exact same configuration. So it will move in a similar way, but your answers would be different. So I would encourage you to try this. Yeah. MATLAB, search inside MATLAB, URDF file. So if you go to robot toolboxes, RAS toolbox, there is a folder with bunch of robots. Each robot has its CAD model and the URDF file. Yeah.
Same kinematics as same design as the furniture that we are using.
Which one?
MECA 500 R3. MECA 500 R3.
500 R3. I haven't looked at this robot.
The documentation for the load robot function of MATLAB.
I don't know if it is exactly same as 200 ID. Then
Like normalized, so everything is in 0 point something, but the overall it is same.
I don't know. So I won't be able to comment if it's the right approach or not, but you can try that and see if your answers match. At the end, you need to match 3 answers. First, your answer coming from the actual robot. This is from the lab exercise. Second, answer coming from your forward kinematics. And you can also try inverse kinematics too, just for the kicks. This is from the MATLAB. And then you will have the solution from the inverse kinematics designer. So you have to show correspondence between these 3. And I think it works because Rajdeep has the solution. So we have the solution. It works. Okay. Any other questions? Yeah.
Is the 200 ID model the same one that's in the lab, the 4S? So there's a couple variants of the 200 ID, and I found the URDF for all of them. I just wasn't sure.
We have 200 ID 4S.
Sorry, the sticker on it says 14L.
Which one is 14? Is it 14L? I don't remember.
That doesn't.
No, the robot actually you made the measurements on.
14L.
14L. Okay, then it's 14L. Because there are 3 or 4 Fanuc robots. So you did the experiment on 14L. Okay, then use that one. Oh, then my bad. Yeah, I want lab to match with the analysis that you have done and the inverse kinematic designer that you have. Any other questions?
If we use a numerical solution and it will give us so many solutions, solver. I mean the numerical solver, and you give us like 3 or 4 solutions. So shall we write it down all the solutions?
Now here is what would happen. That is the beauty of inverse kinematics designer. If you look at the inverse kinematic designer, it allows you to enter the joint limits. So the actual inverse kinematic solution can find multiple solutions, but inverse kinematic designer will see out of those multiple solutions, which is a possible solution, and it will give you that. So if you use your own inverse kinematics solver, The next step here is look at the joint limits and see which joints are possible, which joint angles are possible. So that is the next natural step.
So, do we solve the inverse kinematics from MATLAB too?
Yes.
Or just the inverse kinematics for nine?
If you want, MATLAB has an inverse kinematic solver. It's just like the solve function that we use. Yeah, so it's a solver, but you can use inverse kinematic designer internally is using that function. You can directly solve that, use that function and solve. So, but I mean, then you if you want to visualize, then you will have to add your own visualizer. Okay, any other question? We won't be meeting next Monday, so
Oh, a break.
I will be here. Yeah, workspace analysis is only available in 2024 B. What you wrote your own code for workspace?
It's 2024A.
Yeah, so you can just, but 2024 B is you can update free. So it's just update the 2024 B and that workspace. What?
So I got the Yokogawa and the inverse condition for the analysis, but I don't think the Asada effect.
Yeah.
Yeah.
Do the first two, but not the last one. Do you want all three or do you just want?
It's saying that all the matrix values should be positive, but I'm not sure.
They're all not numbers.
Yeah.
Hold on. No. Let me what silence, please. What's happening?
So for the workspace analysis, there's MATLAB gives 3 different functions to perform workspace analysis.
Uh-huh.
The
Yeah.
Yoshikawa index, the inverse condition index, and the Asada index.
Correct.
You can do the first 2 given the Fanuc robot that we import. The third one returns an error.
Okay, so try that for the Fanuc robot that we have
Okay.
and tell me if you don't get all 3, that's totally fine.
Okay.
Is that the question you had?
Yes.
Okay. But you need to modify the script so that it can do the workspace analysis for your robot. Everyone understood this? Now some of you, yeah.
For the works of analysis, we really have to meet the limits, right?
Yeah. Now, since I wasted so much time. Okay. Now here is something I'm gonna give you as a bonus. Now, if you go to Fanuc website, and register, and they have a software called RoboGuide. So you can go to Fanuc website. You have to register with your ASU email, and they will give you a download link for Fanuc RoboGuide. That software will be valid for 30 days. Okay. And if you do the forward and inverse kinematics for this robot in using RoboGuide, you will get 5 bonus points. Extra. So you can get 15 out of 10. Yes. Yeah. So now this is the bonus. So you can actually have RoboGuide. You want 5 more points? Okay. All right. There is another software which is written by my good friend. That software is called VREP. You can do the exact same thing and 5 bonus points. Yeah. Google. No, so this is what is needed for the current assignment. If you do RoboGuide, forward and inverse kinematics, you get 5 points extra. If you do forward and inverse kinematics with VREP, you get 5 points extra. No, so believe it or not, that VREP software, that whole software visualization was coded by just one person. He's in Italy. Just one student. He started working on that software as his master's, did his PhD, and then he continued to work on it after his PhD. The whole end-to-end software is written by only one person. Yeah, so in case, no, I don't know what it did. So I will show you, since I already wasted so much time. Yeah, sure, but I'm not teaching. That is the problem. So VREP, and at one time he basically made it available for free. So this is the software. Download. So you can actually download the EDU version. Yeah. No. Free trial. Yeah, do the free trial for 30 days. Unless you have $2,500 to spend. So Fanuc RoboGuide, what you do is you need to go here and basically register at the website here, and then they will send you the link to download. But VREP is available for free. You can try VREP. Yeah. Okay. Any questions, concerns, ideas, thoughts? Okay. I was going to start dynamics, but today, how much time? Okay. What I want to do is, so we have discussed robot kinematics. I taught you robot kinematics using, actually we did 3D kinematics using rotation matrices. That technique is very, very powerful. You can do any three-dimensional kinematics using that technique. It doesn't have to be a robot. It could be a bird. It could be a plane. It could be a helicopter. It could be a tilt rotor. It could be a rock. It could be a spaceship. Whatever it is, the technique that we have studied, you can use that, assign the frames, and find out the forward and inverse kinematics solution for that object. Then we looked at the static force analysis. Static force analysis is if you have a robot that is supporting a payload, then how much of joint torques should be so that that payload is supported. If the robot is moving very, very slowly, then the static force analysis works just fine. It means you have a part that you are grabbing from point A and placing it at point B. But if you are doing that motion very, very slowly, the static force analysis would give you correct results, because you are ignoring the inertial properties or accelerations of that object. But static force analysis fails when the motion is fast. For example, you have seen those crazy robots. They are doing pick and place operation. At that time, you need to take into account the dynamical effects or the acceleration effects or the inertia effects, the damping effects and the spring effects to solve that robot. Now, what we are going to do is we are transitioning from kinematics to dynamics. And dynamics is very, very important because most of the robots are unstable systems. Then what we do is we add some type of a control. We can add the linear control or we can add the non-linear control and make sure that robot is able to perform that particular operation in a very controlled fashion. So when the robot is performing pick and place operation, the robot is picking it carefully, dropping it carefully. It's not distorting the object or it's not hitting anything. So we are transitioning into dynamics. And the dynamics starts with something called as Newton's law. And I'm going to start with very basic part of dynamics. Let's start with a coordinate system. So you have X, you have Y, you have Z. And the Newton's second law states force is equal to mass times acceleration. Force is a vector. Acceleration is a vector. Mass is a scalar, which means force has magnitude and direction. Acceleration has magnitude and direction, which means if your acceleration is in the same direction as positive x-axis, that acceleration is positive. If your force is in the same direction as positive x-axis, that force is positive. If your acceleration is the same direction as positive y, that is going to be positive, and so on. Everyone understood this? Now what we are going to do is, we are going to write down the forces and the accelerations on each body. And once we sum all the forces, because understand, this is a vector. You can have forces in the x direction, acceleration in the x direction. You can have forces in the y direction. You can have acceleration in the y direction. You can have forces in the z direction. And you can have acceleration in the z direction. Mass is a scalar quantity. It's just a number. It's going to remain constant. But fx, ax, fy, ay, fz, faz could be positive or they could be negative. Everyone understood this? Okay. So this is called as Newton's second law. So Newton's second law can be stated as you need force to create acceleration. Okay. So you have to add force that would change the acceleration or that would induce acceleration. There is something called as the Redcar's corollary to Newton's second law. So which means corollary means extension. There is Redcar's extension to Newton's second law. And that goes like this. And I want you to remember this. Sometimes force alone is not sufficient to cause acceleration. Sometimes force alone is not sufficient to cause acceleration to induce motion. What it means is you have an object that is stationary, you apply force, but the object does not move. In other words, you have a person who has a lot of inertia. No matter you tell him, okay, come on, do this, do this, do this, that person is not moving. Okay. In that case, you need a jerk. What that means is you take the derivative on both sides and you have df by dt is equal to m dA by dt, and this guy is called as jerk. Okay, now this will be clear. So you have a person that's not moving. You push, you push, you push. And what do? You give a jerk. It means to actually give a rate of change of force. It's an impact. Rate of change of force that gives you jerk and things start moving. If you work on cars, many a times you always are against some stubborn bolt or maybe a fastener that does not come out. No matter you pull, the things does not come out. What do? You take a hammer and hit it. So basically, you induce the jerk, and all of a sudden, things are moving again. Remember that. Not always, but sometimes in life, to get things moving, you need a jerk. Okay, that being said, now let me take the very simple example that you have a spring and you have a mass. Now, this spring is a linear spring. What do I mean by linear spring? That if you add what linear spring means, one burger for $1, two burger for $2, three burger for $3. Non-linear spring is one burger for $1, two burger for $2, and five burgers for $3. So what you have is you apply the force and the spring displacement is proportional to the force. So this is your F1, this is your F2, you have delta 1 and you have delta 2, and this force F1 is proportional to delta 1. This force F2 is proportional to delta 2. In other words, the force has a constant factor that is multiplying the displacement. So force is proportional to displacement, and this K is called as the stiffness. So sometimes you have a softer spring, which means the same load, the spring deflects furthermore. Sometimes you have a hard spring, which means the spring does not deflect for the same amount of force. So if you apply force and displacement, if you apply force and you measure displacement, if you plot this, this gives you a straight line. This slope is called as K, which is called as the stiffness. Everyone understood this? Yeah.
Is there a parallel sequence where you're multiplying by constant?
The stiffness is always going to be constant. So we are not talking about the springs that change stiffness. There are some springs that basically harden or soften, but our spring is ideal spring. It doesn't harden, it doesn't soften, and it's linear. So if you apply 100 newtons, it will deflect by 100 millimeters. If you apply 1000 newtons, it will deflect by 1000 millimeters. Everyone understood this? Okay. Now what I'm going to do is I'm going to apply the force in this direction. So acceleration, displacement is going to be in this direction. Velocity is going to be in this direction. Acceleration is going to be in this direction. And it's extremely important. Force is going towards right. So I try to move it. So the displacement is towards right. Velocity is towards right. Acceleration is towards right. Do you agree with me? The spring would be deflected. So this spring will get extended. So this spring will be extended. And what would happen is the spring would exert the force which is equal to the stiffness of the spring multiplied by the displacement of the spring. Mass is displaced right by X amount, which means spring will be stretched by X amount, which means the spring would be pulling the mass back by stiffness multiplied by the displacement. So force is given in newtons, stiffness is given in Newton meter, multiplied by meter. So I have the force on the right, force on the left. Everyone understood this? Once again, extremely important to note that force is going towards right, which is in the positive x direction. Displacement going towards right, positive x direction. Velocity going towards right, positive x direction. Acceleration going towards right, positive x direction. Everyone understood this? So these all quantities are positive. On the other hand, the spring is pulling the mass back. The spring is pulling the mass back. So the force that is given by the spring is k times x, is in the opposite direction of positive x-axis. Everyone understood this? So now I want to apply Newton's law. Newton's law is force is equal to mass times acceleration, and this everything is in the x direction. So what I'm going to do is, do you agree with me? X double dot is my acceleration. So, and I'm going to write down the forces. I see that there is only one force, k times x. And if I draw the free body diagram, I see kx is in this direction, and I see x double dot in this direction, and the mass is m. So I would have minus k times x is equal to m x double dot, which means this equation is mx double dot plus kx is equal to 0. This is called as the differential equation of motion. Which force? Oh, actually, so, okay, you are absolutely right. I should be writing F over here. But what I want to show here is, think about this like this. Think about like you pull the mass towards right. You pull the mass towards right and let that mass go. Pull the mass towards right. Let's add F. You're right. So let me add this F here. Let me add this F here. So now what I want to do is, I want you to understand this is called as the differential equation of motion. Mx double dot is the inertia term, kx and F, these are the forces. This is the force in the spring, which is actually an internal force, and F is the external force that I have applied. Now, this is called as the differential equation. Why this is called as the differential equation? Because please note that the independent variable is t, and the dependent variable so there are three dependent variables. Dependent variable is x, x dot, and x double dot. Do you agree with me? Now, for the sake of discussion, let me take an example where F is equal to 0. Let's say I remove the force F. Then my equation becomes mx double dot plus kx is equal to 0. So I want you to visualize this. Assume that there is no damping, there is no external resistance. What I have is, I have this spring attached to the mass. I pull the mass and let go. What would happen? That mass would continuously oscillate back and forth. If there is no friction, there is no damping, there is no dissipation, this oscillation will continue for the infinite period of time. Do you agree with me? Okay. So what I'm going to do is, I'm going to kind of try to show this. So you have this spring, you have this mass, this is K, this is M, and this mass is going to go from one extreme point to the other extreme point. And I can guarantee you most of you know this, but I want to explain this from physics point of view. So this mass is going to perform something called as the simple harmonic motion. So which means it will go up and down, left and right, depending upon where that mass is located. So it's gonna go towards right and left, right and left, right and left. Everyone understood this? Now this actually throws light on a very, very fundamental principle of engineering. And this is the principle on which the universe operates. I want you to pay attention. Why does, and it's extremely, it's simple, but conceptually it's very interesting. So please try to understand. Why does this mass vibrate? You pull the mass, let it go, it oscillates back and forth. You have the spring, you have the mass, pull the mass, let it go, it oscillates back and forth, up and down, back and forth, up and down. Why does that happen?
Energy.
Energy, momentum, equilibrium is disturbed. Equilibrium means everything is steady, nothing is moving, nothing is changing. Now here, initially the mass was in equilibrium position. I agree. I pull the mass, let it go, and it continues to oscillate back and forth for the rest of our lives.
Inertia of motion.
Now, why does this happen?
Conservation of energy, like it's potential energy to kinetic.
Okay, now the conservation of energy, and let me explain why this energy is extremely important. So understand, there are two extreme positions. This is position A, this is position B, and this position C is an equilibrium position. So what's happening? As I pull the mass continues to go towards right. At the extremity, at point B, the mass changes the direction of travel, which means when the mass is at point B, at that instant, its velocity is zero. So you have the velocity of the mass decreases, it becomes zero, and then it starts increasing. Do you agree with me? What it means, at point B, the spring is fully stretched, but the velocity of the mass is zero. Spring is stretched, which means it has the maximum potential energy, like a recoil. So you have the maximum potential energy when the spring is fully stretched. So at point B, potential energy is maximum. Kinetic energy is zero. Why kinetic energy is zero? Because mass is reversing. So at that moment, the velocity is zero. Same thing happens at point A. Potential energy is maximum because the spring is fully compressed. And the kinetic energy is zero because the mass is going to reverse. So which means at that point, the velocity is zero. On the other hand, at the center, spring is neither stretched nor compressed, but the velocity is maximum. So which means the potential energy is zero and kinetic energy is maximum. Do you agree with me? So this energy interaction, extremely important. This energy interaction is causing this mass to oscillate and back and forth. And if I don't have any other energy dissipating element, this energy interaction will continue for infinite time period. Everyone understood this? What it means is I can use this energy principle to derive the equation of motion. I tell you the challenge with the Newton's law. Newton's laws work when Newtonian physics is applicable. Newton's laws don't work at quantum level. Newton's laws don't work when you start approaching speed of light. But energy principles always work. Energy interactions are the fundamental interactions in universe. So if you look at the Hamiltonian principle, if you look at the Lagrangian principles, all these principles or variational techniques are energy methods. And energy methods, they are beautiful because energy is a scalar quantity. You don't have to worry about the direction of forces. You don't have to worry about the displacement. You can start with a scalar quantity and derive these beautiful equations. Let me give an example. Everyone agrees here, and the concepts are extremely simple. If you are from electrical engineering background, energy principles are the fundamental quantities that define the whole Lyapunov approach for stability. So I want you to understand this simple thing. Tell me that is energy changing? So here the sum of potential and kinetic energy is remaining constant. Sum of potential and kinetic energy remaining constant. Sum of potential and kinetic energy remaining constant. Which means throughout this oscillations, the total energy is remaining constant. Everyone understood this? Okay. So what I'm going to do is extremely important because some of you may take, if you are from electrical background, you will take linear systems where you study the Lyapunov approach. Lyapunov approach for stability comes from this, from energy interactions. So what I can say is, I can say total energy is equal to potential energy plus kinetic energy. Do you agree with me? Potential energy is nothing but you have this force, displacement, and this is the energy stored in the spring. So if you see that the energy stored in the spring is F times delta multiplied by half because it's a triangle. F is K times delta. So K times delta square half is the energy stored in the spring, potential energy. Do you agree with me? Now what I'm going to do is, I'm going to write down the expression for potential energy, 1/2 K, since my displacement is X, I would say 1/2 Kx square. Do you agree? Kinetic energy is 1/2 mv square, which is given as 1/2 m, v is x dot square. This is total energy. The total energy is remaining constant, which means the derivative of total energy is 0. So what it means is I take the derivative of total energy. So derivative of this guy is 1/2 K. Now remember, X is a dependent variable. The independent variable is T. So I have to use UV rule. Do you agree with me? So this becomes 2x multiplied by the derivative of x, which is x dot. Everyone understood this? Remember, the independent variable is T. Dependent variable is x. We are differentiating x square. So it's going to be x square derivative multiplied by derivative of x. So 2x x dot is what I have over there. Same thing is going to happen over here, which is 1/2 m 2x dot x double dot. Do you agree with me? What? X dot square, if I take the derivative, is going to be 2x dot and derivative of x dot, which is x double dot. Everyone understood this? Now, the rate of change of total energy is 0. So I will, which it means k x dot plus m x dot x double dot is equal to 0. Now I cancel this guy. and I get the same differential equation as we derived earlier. Everyone understood this? If you study Lyapunov's function or Lyapunov's stability criteria, what they do is they come up with a Lyapunov function that resembles the total energy of the system. If the total energy of the system is remaining constant, which means if the derivative of total energy is zero, very important. If the derivative of total energy is zero, the system is a simply stable system. Which means I'm going to call this this function v. So v dot is equal to 0. Equation is simply stable. If v dot is less than 0, then the system is asymptotically stable. And if your v dot continues to increase, then it's unstable. Now, what that means is if some of you are taking linear algebra, and I have 2 minutes and I will explain this in 2 minutes. So please pay attention. Remember that you have a function x dot is equal to ax. You want to solve this differential equation. So this equation is dx by dt is equal to ax. How do you solve this? Integrate both sides. When you integrate both sides, what you are going to do is you are going to have dx integration is equal to integration ax dt. Now, what this means is you are going to have x of t is equal to, sorry, I need to have, I jumped a step. So this x dx by x integral is equal to integral a dt. This is going to become ln of x is equal to at plus c. Now, if I take the exponent on both sides, it becomes x of t is equal to e to the at, e to the c. E to the c is a constant. So this x of t is equal to, you are going to get this constant a and e to the at. Do you agree with me? Any questions about this integration? Now imagine if your a is 0. If your a is 0, you agree with me, x and t. If your a is 0, x would be at a and it will continue to stay at a. If a is positive, this small a, this is a is equal to 0. If your a is positive, this is what will happen. If your a is negative, this is what will happen. Do you agree with me? Now I want you for a minute. A is equal to 0 is simply stable case. A is greater than 0 is unstable case. A less than 0 is asymptotically stable case. Now what happened? Here is the enlightenment. This equation x dot is equal to ax, small ax, is just one equation, which means a could be 1, 2, 3, 4, 5, 6, 0, -5, -10. Do you agree with me? And the sign of a dictates whether the system is unstable or stable. Do you agree with me? Now, if you study linear algebra, what you have is you have a matrix A, right? And eigenvalues of the matrix dictate the stability. If the eigenvalues are zero, they have zero real part, the system is simply stable. If the eigenvalues have positive real parts, the system is unstable. If the eigenvalues have negative real part, system is asymptotically stable. Remember this. I will stop here.